Hi, everybody. I'm going to talk a little bit about localized versus delocalized lone pairs and how they relate to resonance in this video. So it's important to be able to recognize kind of when a lone pair is stuck on an atom versus when a lone pair is moving through resonance. So first off, a little bit of vocab here. For a localized lone pair, we're not able to participate in resonance with those lone pairs. Okay, we're essentially thinking about it being stuck or localized on one particular atom. So it's not going to be doing any resonance or anything like that. This lone pair will always inhabit some sort of hybridized orbital, so an sp3, an sp2, or an sp orbital. Delocalized lone pairs, on the other hand, they can participate in resonance. Okay, we're essentially thinking about them as being able to move around or delocalize between multiple atoms. Okay, the only way to do that is they have to be inhabiting a p orbital. Otherwise, it's not possible for them to actually be delocalized lone pairs. So with that, we want to always keep in mind here that resonance only happens through p orbitals. Okay, so if you've got a lone pair that you are incorporating in some sort of resonance structure, that lone pair must reside in a p orbital in order for that to happen. So let's look at a couple of examples here. So let's look at this. The compound on the left, I'm going to call it compound A, and then B. So A is diethyl ether. We're going to learn nomenclature soon, but I'm going to start saying the words so that they start getting heard. So A is an ether, B is an ester. I know that those are very close, but they are very different. It is something that takes some time to figure out and practice and get good at. So for A, let's go ahead and draw in all of our lone pairs first. So we've got two lone pairs on that oxygen because we've got two bonds, so we need another 4 electrons. Same thing for the electrons over on B, or the oxygens over on B, excuse me. So I have all of my lone pairs drawn in now. So essentially, we kind of need to think about this as one lone pair at a time. So if we're looking at A, if we're wanting to know whether a lone pair is localized or delocalized, we mostly need to look at, can I do resonance with this lone pair? So on A, we're really looking at, am I going to be able to move those lone pairs anywhere else? If you draw in your H's, you quickly see, no, I cannot. Okay, because if I've got an sp3 carbon right here on both sides, then I'm not going to be able to do any kind of resonance with those lone pairs. So with that, then we know that both of these lone pairs are localized. Okay, if we want to know what orbital they are in, we first need to determine the hybridization of our oxygen. So the oxygen has 1, 2, 3, 4 things around it. It is sp3 hybridized. That means that the only orbitals that it has are sp3 orbitals. So both of those lone pairs are in sp3 orbitals. Okay, so let's go ahead and look at compound B. So in B, I have different lone pairs kind of in different environments here. So we're going to take it one at a time. The first one we'll look at is, we'll look at this lone pair first. Okay, and in that, we're kind of looking at this one as well because they're been in pretty similar environments here. So if I'm looking at that, I want to see if I can do any resonance with them. So the only direction I can really go is this way. Okay, if I do that resonance structure though, I will be expanding the octet of my carbon atom, which is not allowed. Okay, so essentially what we're looking at here is these two, you're going to run into the same issue for both of them. These are both localized. Okay, so the red ones, or the orange, I think this is orange, the orange lone pairs So if we're trying to figure out the orbitals again, we need to determine hybridization of that oxygen. So this oxygen has 1, 2, 3 things around it. So it's going to be sp2. The sp2 does have a p orbital in it, but that p orbital is already making that pi bond there. So essentially that p orbital is already serving a purpose. So these two lone pairs are in the sp2 orbitals. Okay, so if I look at my other oxygen, so I'm going to switch over to green for these ones. Again, we're going to look to see if we can fulfill any of our resonance patterns here. So if I have, we'll look at this lone pair right now. So if I have that lone pair, I do have a pi bond nearby where I can think about doing some sort of resonance move like that. Okay. And I'm going to draw the original two lone pairs in orange there. Okay. So essentially the lone pair that I've kind of moved, this lone pair used to be the pi bond. This used to be a lone pair. So you can kind of track where things are going a little bit. But this is a perfectly reasonable resonance structure once I add my lone chart, my formal charge. So this is a reasonable resonance structure here. So that means that if that's a reasonable resonance structure, then that lone pair is delocalized, which means that it has to be in a p orbital. Okay, because if we are participating in resonance, again, that means p orbitals all the way. Okay, so let's go ahead and we'll circle this one in a different color. So this one is in a p orbital because we are able to do a reasonable resonance structure with that lone pair. So the part where it gets tricky is when you're looking at the other one. Okay, so if we're looking at this other side, really what we're saying is, can we delocalize both of them at the same time? So at that point, you're saying, can I do this on this resonance structure? The answer to that is no, you cannot, because you're going to be overloading that octet again on that carbon. So essentially what we have here is this lone pair is a localized lone pair, right? Because we have one lone pair that can't move through all the resonance structures that we have drawn here, okay? So this falls into the same category essentially as these two, where we have them in an sp2 orbital, because if we're looking at this oxygen and trying to figure out its hybridization, it gets a little bit tricky here, because if you look on this side, you would say 1, 2, 3, 4, that should be an sp3 oxygen. So when we're looking at this and we ask ourselves, is this sp3? The answer is no, because if I can do resonance here, we're really looking at this oxygen as being sp2 because I'm making a pi bond, right? So my lone pair is in the p orbital to make that pi bond in that resonance, in that resonance structure. Okay, so that's something we really need to be careful of, that we're really looking carefully at resonance possibilities when we're determining hybridization and looking for these delocalized lone pairs, so that we're not accidentally going, oh, oops, that should have been an sp2 instead of an sp3 because I've got this delocalization. Okay, so we really want to be looking carefully at atoms with lone pairs that are next to pi bonds. Okay, so that's kind of going to be a good rule to follow, because as we saw up here, those lone pairs that are on an atom that are already part of a pi bond are generally going to be in those hybridized orbitals that are not delocalized. They're just a localized lone pair. But the ones that are next to the pi bond, those are the ones we kind of need to look out for. But I said this word reasonable up here, and I think we should talk a little bit about how to tell if a resonance structure is not reasonable. So I think that's kind of easier than showing what's reason. There's a lot of reasonable, but there's kind of a limited selection of unreasonable ones. So let's go ahead and look at these examples really quick. So I'm going to go through this one. Oops, I don't want that black. Ooh, I want that black. Okay, so I have the nitrogen lone pair. I'm going to draw in all of them real quick. Okay, so I have all my lone pairs drawn in. So again, we're going to do the same kind of process here, where we want to think about, can I do resonance reasonably with these structures? Okay, so I have that as a resonance structure. That all looks pretty reasonable. So again, this is going to be a delocalized lone pair. Oops, let's not do that. So the green one is in a p orbital again. Okay, if we look at our other example on the right-hand side, we have another nitrogen that looks very similar to that, where we can go here, here, right? So this one is going to be a similar option, where that is going to be in a p orbital. But let's look at this nitrogen, okay? For this nitrogen, we technically do have that nitrogen next to a pi bond, right? It is next to this pi bond here. So what happens if I go and do this resonance structure? Okay, I'm not breaking any of my charge rules. I did all the right arrows for my electron movement, but there is something that should be making us feel a little bit uncomfortable. So if I do this, that nitrogen would be sp hybridized, right? Because now I only have a steric number of 2, because I've got this carbon and that carbon. So I only have 2 things around it. That's the only way that I could get 2 p orbitals, right? Because that nitrogen is now part of 2 pi bonds, which is what I would need in order to get this lone pair to be delocalized. However, an sp hybridized atom needs to have a bond angle of about 180 degrees, right? That's going to be really, really hard to fit in this little ring, okay? So this is a big old yikes if we're trying to do this in a ring. Okay, so this resonance structure is not reasonable. Okay, if we're trying to put sp hybridized atoms into small rings, it's really a no-go because that bond angle is just not going to allow that 180 degrees that is necessary. So then if we go up to this one and finally label it, so this is going to be localized. That nitrogen, we're considering it as the sp2 orbital, as the sp2 hybridized, so because we've got 1, 2, 3 things around it. We're not delocalizing that lone pair here. So it's sp2, and it's going to be in an sp2 orbital. Okay, so again, this will, as everything we do, is going to take some practice. And let me know if you have any questions, and I'll see y'all later.